Today, I will give a talk about an interpretable non-interference measurement and its application to processor designs. In recent years, both software and hardware systems become more complicated than before. The risk of unintended information leakage grows with the use of secrets in those systems. To achieve some functionalities, a procedure is not guaranteed to leak nothing about a secret, as it usually won't output a complete random value not dependent on its input. Furthermore, some developers may already notice the issue, but they may misestimate the risk due to the lack of formal measure. An example of misestimation is a cache-based side channel in processor designs. Although we already noticed the potential risk many years ago, most of us choose to underestimate it before the Spectre and Meltdown works become published, because it's hard to brainstorm the quantitative leakage without an automatic tool. To build a tool to measure leakage, we first model the information linkage under a system with procedure. A secret variable S is designed to be close to unauthorized users. However, the implementation may include some unexpected information flows transferring the secret to attacker of the walls, which cause the interference. To be worse, the attacker can modify attacker-controlled inputs to the procedure to enlarge the linkage. Besides the secret and attacker-controlled inputs, a procedure may have other inputs that are not considered as secret but are unknown and not controlled by the attacker. To motivate you about how to relate the interference with information leakage, here we will first consider a very easy attack task. Given two different secret values, S and S', the attacker will control C and observe O. So the CO tuples that are possible the secret value S will compose the attacker's view for the secret S. If the attacker's view for S and S' are completely different, the attacker can easily distinguish between S and S' using O. If the attacker's views are completely overlapped, that means the attacker knows nothing about whether it's S or S'. When they are partially overlapped, we propose to use the J-card distance to measure the difference between two secret values. However, the J-card distance considering two secret values would be only sensitive to how often the interference happens, but not sensitive to how much it could leak. To measure leakage in various dimensions, including how often and how much information leaked, we propose to measure the interference between two secret sets. Thus, the attacker's view YS includes all possible CO tuples for the secret value inside of set S. And when the secret set size is small, it will be more sensitive to how often the secret leaks. When the secret set size is large, if the J-card distance is still high enough, that means the attacker could be able to distinguish between two large secret sets, and the attacker could use the outputs to largely narrow down the guessing space. And thus, once that happens, there should be much about the secret to leaked. Until now, our framework is general enough to both software and hardware evaluation. To evaluate hardware modules, besides the difference in coding, there are several challenges when analyzing information leakage in such complicated scenarios. First, due to the complexity of the hardware, there are many possible flows to various of hardware registers would cause leakage, but not all of them are real leakage. Second, the linking logic involves both software and hardware. If we use codes to explain, it's hard to summarize the cause from both software and hardware codes. If we use example to explain the leakage, it's easy but too ad hoc to a special case. To avoid considering unknown source of interference, I propose to support declassification in quantitative measure. Typically, declassification is used to rule out allowed information flows when checking or verifying a security property. Different from prior works, we use declassification in a different way. So we not only remove the allowed interference defined in the classification rule, but also try to include the potential interference caused by the combination of the existing observable and the declassified information. To use the declassification in our measure, I defined delta to represent declassified variables. Then the classified information delta is available to any users, including the attacker. First, the attacker could read the delta as it's allowed. Thus, I changed my leakage measure so that the attacker's view includes all C/O delta values to distinguish a secret. This step enhances the attacker's power. Second, since the interference caused by the delta itself is allowed, when using the C/O delta tuple, I will not consider the tuple when C and delta is not possible for S prime, as that interference is allowed by the delta defined in the ds delta. So that is, the shadow arrow will not be included inside of the attacker's view set. Similarly, I also removed the allowed interference in the attacker's view for S prime, and both steps removes allowed interference from our measure. That is, the update sets will only consider in case when C and delta are shared between S and S prime. We update the J-card distance measure using the new unit sets and intersection sets to evaluate the information linkage with user-defined. Next, to automatically summarize the logic cause of the leakage, besides the quantitative measure, I will use interpretable machine learning to explain the joint hardware software logic in a clean way. The high-level idea is to train an interpretable classifier to tell whether the secret pair S and S prime will cause interference. The logic of the classifier will be able to tell when the attacker chooses some secret controlled variable C, the observable for the S and I is not possible for any execution with S prime. And this classifier will output label IS or NS representing interference set or non-interference set. To train the model, I will generate input pairs causing interference and follow non-interference. Here I will present how to generate input pairs causing interference. To cause interference, the attacker's view CO and delta should be feasible for some secret S, but it's never possible for another execution with a different secret value S prime. Another constraint is to allow the interference caused by the classification rule, so that we should assume that the S and S prime shares the declassification value. To support more easy-to-understand relationship between variables, we first do some feature engineering before feeding them to the model. I first will reconstruct the value in tuples based on their original type, and then use a local linear model to find some potential useful combinations of variables. The basic idea is to pick some anchor points and then train the linear model using the data close to the anchor. A natural model we can consider is the decision tree, as its if-else style decision is very close to human thinking. However, such decision tree grows deep and complicated quickly, thus it may not be able to explain the logic in a very clean and high-precision way. To avoid deep and overfitting tree, we choose to use gradient boost tree to generate decision trees in symbols, which use many trees together to make decision. Thus, we need to explain multiple trees. In order to explain multiple trees, we compose a rule per path from the root to the leaf in a tree. The rule will have an associated precision and recall rate to indicate the quality of this rule. Only a rule with high precision and relatively high recall rate will be considered. A list of those rules ranked by precision and recall would help users to understand how the interference happens. The foundation of the tool is counting and sampling, as we need to count attacker's view for measurement calculation and sample input pairs for the interpretation. To make the counting and sampling scalable, we use hash-based approximation. Specifically, we apply random hash constraints on the counting and sampling target variables. Then that task is only responsible for a subset of solutions. To compose a set of secret values used in the measurement, we also applied hash methods to compose a random secret set. And using hashing in this way allows us to distribute a task to multiple small sampling and counting tasks using the universal hashing, and thus it will be scalable horizontally across different threads and cores. To support the hardware security evaluation, we design our toolchain in this way. First, the software code will be translated to a sequence of corresponding assembly codes as an input to the memory inside of CPU. Instead of using speculation, I will use a logical translation provided by the USIS to directly translate the Verilog specification to SMT2 formula. The translation will generate the logical formula for one cycle state transition and the initialization logic. Then I can incrementally compose the formula for multiple cycle execution with reasonable simplification by stitching the transition logic cycle by cycles. With that post-condition, we can apply declassification and then use model counting to measure the linkage, and use hash-based sampling to generate inputs used for training the interpretable model. Using our framework to set up evaluation for a boom core, for example, I use a tiny configuration for a boom which reduces the memory and cache size and excludes some uninterested modules from the evaluation. Then we symbolize some registers inside the cache and branch predictor and set them attacker controlled. To measure the cache-based side channels, I also make some registers representing the cache hit or miss, observable to the attacker. Using that setting, I evaluated various linkage through cache-based side channels in Boom. First, I compared the normal set associative cache with some normal side channel resistant cache designs, using our customized Boom core, which supports both scatter cache and phantom cache. I also tuned the number of cache ways and sets to see how those configurations affects the linkage. Second, I explore the cache-based side channel leakage in modular exponential function, which is commonly used in crypto algorithms. By comparing the linkage in different sliding window size, developers could understand which parameter value would link the list. A more complicated case I evaluated is Spectre attack. The Spectre attack could trick some error-free programs and break the security barrier designed in the software. For example, here, the software used two arrays, array 1 and array 2. To avoid the user to access out-of-boundary memory, it has a boundary checking so that the access is only available when the offset is smaller than array 1 size. That is, the secret value located outside of array 1's boundary should never be accessed. However, no matter whether the offset is within or outside the boundary, the CPU may speculatively execute the left branch if the predictor thinks it should take the left. That is, the attacker could input arbitrary offset to access arbitrary secret contents. Then, these secret contents could be used as an index to access some data inside of array 2. Although the CPU would revert most changes when a missed prediction is detected, such reverting process does not revert the cache state. So the attacker would be able to use cache-based side channel to infer the secret value. Using the security model, the secret variable is the targeted memory contents. The offset variable and the branch predictor is attacker controlled. The size for the array1 and the cache hit limits for the attacker controlled memory blocks are observable. Since we don't care about in-boundary memory linkage, we also need to define a delta to allow the declassification for the in-boundary value. In order to trigger the speculative execution, the branch checking should be delayed when resolving it, which is usually due to some flow dependencies. Specifically, I present two code snippets called different data dependencies for branch checking. One will cause a very long speculative execution window due to the expensive arithmetic logic units, multiplier and modular units. Another procedure causes a relatively short speculative window just due to a memory accessing to array1 size. I also tested when I inserted a fence into the code as a mitigation to disable the speculative execution. And our evaluation is inside of BOOM version 2.2.3. Without declassification, the curve for short and fence cases are very similar, while the curve for the non-speculative execution case is very high. And after I apply the declassification that is used to allow the in-boundary linkage, the procedure with non-speculative execution window is just slightly decreased, while both short and fence cases cause zero linkage. This is because since BOOM version 2.2.1, the cache module starts to track the speculative execution status, and if the speculative execution window is not known enough, the module would discard the refill request if a misprediction detected. When we tested procedures in an earlier BOOM core, then the curve for a short case is very close to a long speculative execution case instead of close to the fence mitigation case. Due to the joint software and hardware logic, understanding how the interference happened is hard without domain knowledge. Using interpretable machine learning, we could generate a list of logical rules causing the interference. First, we use a local linear model to generate some linear feature. Here, we have a linear feature that representing whether the offset value is higher when next than the array1 size. The first feature we use inside the rule indicates that the offset is higher than array1 size. The second predicate inside of this rule is about the controlled variable. It indicates that the state of the branch predictor should be set to not taken. The reason to have this condition is because we ruled out in-boundary linkage. To cause the interference, the rule also requires that some bits in secret is different from another secret value. For this example, multiple rules similar to that will be generated, and those rules together will indicate that when the branch predictor is carefully set to a specific state, the secret bits from bit 0 to bit 3 would be linked when the offset is out of the boundary. Here we evaluate the performance of our framework using different workloads. The first figure shows the runtime used to compute one estimation for the J-car distance measure using different workloads. The measuring runtime varies from less than seconds to 20 minutes. To generate the interpretable rules, the second figure lists the sampling process to generate tuples for interference set and non-interference set. And it shows that each tuple could be generated within seconds. And thanks to the use of universal hashing, both counting and sampling process could be highly distributed. That is, if the cloud computing grants us unlimited number of cores and threads to do this computation, Given a procedure logic, we can finish the analysis within minutes. Thank you for joining my talk. Feel free to chat with us in Slack if you have any questions.